Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending today's presentation on mastering corona treaters for film extrusion lines. This is part one, how properly defining your application determines the right corona treater for your operation. If you have any questions during the presentation, please use the GoToWebinar question tool. You may submit a question at any time during the presentation, and we'll reserve time at the end of the webinar to answer as many questions as we can. Please note that this webinar is being recorded, and you'll be able to access both the recording and presentation slides once they are available online within 24 hours. As I mentioned, this is part one in a three-part webinar series. By registering for this first webinar, you are automatically registered for the second and third events. You will receive your credentials for each of these webinars in an email tomorrow. On June 7th, we'll be covering how to optimize your line layouts and drives for repeatable success. And on June 21st, we'll provide expert insights for troubleshooting film extrusion application issues and also share useful maintenance tips. If you have colleagues who would benefit from attending this series, please refer them to our website as listed on this slide, or simply email me and we'll help them register for the webinar series. Today, we are very fortunate to have Enercon's Vice President of Application Engineering, Tom Gilbertson, as our presenter. Tom is globally recognized as one of the most knowledgeable experts in the field of surface treating. With over 35 years of application experience, Tom has authored numerous technical papers and articles on surface treatment and is a frequent presenter at industry events hosted by organizations such as TAPI, the Roll-to-Roll Converters Association, formerly AMCAL, ICE USA, and the Flexographic Technical Association. In today's presentation, Tom will give you a behind-the-scenes look at how Enercon uses your application parameters to determine which technology options will best serve your operation. With that, I'll pass it over to Tom.
Thank you, Mark. Good morning, everybody. I'm happy that you're joining us today. I'm looking forward to presenting this information to you, and I'm anxious to also get some of your feedback and questions and going forward with the presentation. So today we're going to have this overview where we're going to talk about surface treating basics and how we use your application data, and then of course have the question and answer portion. And so to start things off, to make sure we're all starting from the same spot, we're going to look at a very basic understanding of what a corona treater system is comprised of. And essentially it starts with the power supply, and you see it up there in the upper right on this illustration. That power supply takes your plant utility and converts it, chops it up, inverts it, and then it comes out of there at a higher frequency and higher voltage than what it came in at. That then goes to a high voltage transformer, which again boosts the output power, or output voltage rather, even higher, which is connected to a electrode assembly that's typically mounted above a insulated grounded roller. That roller then is supporting a moving substrate that goes across it, and in that gap between the face of the electrodes and the surface of the ground roller and the film is where corona is generated. And that corona that's formed in there is essentially just ionized air. So if someone asks you, hey, what is corona anyway? For those of you who have corona treaters or have experience with corona treaters, that is the short answer to that question. Corona is really nothing more than ionized air. That 10,000 volts at 20 or 30 kilohertz energy that comes out of that transformer and that's connected to the electrode, that is what's the basis of the process, and that's what then changes the surface energy of your particular film. And looking at this at the next slide, you know, when we did this slide a long time ago, it didn't occur to me just how much future benefit this slide would have, because one of the most common questions we get back then and today is, well, I can't see a corona treatment. You know, what does it do? And we're visual, right? We like to see things, and then we can context them and understand what the process is actually doing. So in the day, we actually took at this time it was a 6-color press, process image that was created and then put on this press for printing, and we shut the treater off in between the run. So you can see on this sample on the left, the treated side, but the treated portion and the untreated portion. And what you're actually looking at here is wetting. The important takeaway from this illustration, this photograph, is wetting. All corona treatment, all plasma treatment, all flame treatment, all these treatments that you've heard of, or maybe that you've actually even used, their number one function is to get a liquid to wet the surface. And you might say to yourself, well, I don't get it. Why is that important? Well, if you look at this image, you can see the importance. The top part of the image, when treated, the ink wet. The bottom part of the image that was not treated looks like that. The ink did not wet. And if you look at the illustration on the right, we just sort of illustrated this to show the same thing. So when you have an untreated surface, the ink or the coating or the adhesive or whatever the method that we're taking this treated film to, it will just sit on that surface and sort of ball around, as opposed to a treated surface, which the ink will actually spread and wet. So that really is the main purpose of a corona treatment, is really to get the surface energy up so that an ink, a coating, an adhesive, something will actually wet the surface. So how do we know all this, right? What do we do to make sure that the type of treater that is quoted or that is offered on a film extrusion line is the correct one? As many of you know, there are a lot of permeations of corona treating equipment, right? There are all kinds of names and marketing jargon and all sorts of things. Well, one of the ways we do this is to define your application. And when we say define it, what we mean to get into the weeds a little bit about the product that you're trying to treat. So in the case of a blown film line, for an example, we want to know the type of film you're trying to make. Is it a polyethylene? And then further, is it a low density, a linear low density? Is it a high molecular weight, high density? What is it? What kind of films is this film extrusion line that you have? What is its primary materials that it's going to make? And then secondly, and cooperatively with that, what are the additives in these films? Is this a highly loaded slip modified film? Does it have a lot of anti-block in it? Is it a cavitated film? Does it have calcium carbonate in it? On and on. There are a lot of little details here on film construction that can affect the sizing of a corona treater. And in addition to the sizing, that's just the type of corona treater. Further, we need to know how many sides of the film are treated. So on a blown film line, we'll use that as an example. I have a tube, right? I blow this big tube up. I take the air out of the tube, I collapse it. Now I have this lay flat, as they call it in the industry, that traverses its way down from the primary nip and typically into the treater at that stage. And most of the time at that stage, it goes through a two-sided treater. And they do that because they want to treat side A and side B of this tube, because when the film exits the treater, the sides of that tube get slit, and as the film goes down to the winders, they will end up with two rolls of single side treated film that they can use for their own converting, or they can sell it to a converting operation outside of their business. So it's important for us to understand the number of sides you're treating, what configuration is actually coming into the treater. So let me give you one other side part to that discussion. What if you were to say to me, yeah, wait, we're not going to treat this as it's a tube, Tom, we want to treat this in sheeting form, meaning that after the tubing is slit, we're going to separate that into two sheets, and then I want to treat it. Well, it's really the same thing. I need to know then at that stage of each side of each sheet, are we only treating one side? Are we going to try to treat both sides? Do you want the ability to treat either side, right, before you wind it? So that's another element. The sides treated and in a film extrusion line can get a little deep, right? There's a lot of options that are out there. And then the next step is, which is a critically important specification for corona treaters, and that is the line speed. And in line speed, we really need an accurate, reasonably accurate value from you because everything is based off that line speed number. So once I know the treat width and I know the number of sides we're treating, we will do a calculation in addition to the line speed value you give us to determine how much power it's actually going to take at that line speed to provide you the adequate treatment for your particular film. And so the line speed is pretty important. So what I would suggest to you is think about that a little bit. Don't give an off-the-cuff answer, and consider your entire product line. So let me give you an example of what I mean by that. Let's say we have a line that's basically a mono line, and we, which probably don't have too many anymore, but let's just use this as an example because it's a simple example. And let's say we can run anything on this line from, let's say, 1/2 mil up to 5 mil material. Well, for those of you out there that run film extrusion lines, you know that the line speed is quite a bit different between 1/2 mil and 5 mil. And so you got to look at that product mix you have and then establish what's 90% or 95% of what you do, what fits into that category of line speed, right? So if most of the time you're running 1/2 to 1.5 mil film, and just the fringe amount of time you're running the thicker film, give us the faster speed, because then I'll make sure that the power supply and the related hardware around it all is suitable for that application. So you want to make sure that the line speed is accurate, because if it's not, if the line speed is sort of out there, in whatever land, that's going to then require the vendor to provide you a bigger power supply than necessary, which then will necessitate a bigger treater roll, a bigger frame, potential drive and nip considerations. In addition, when you add all that stuff up, your system cost for that Corona treater just sort of exploded. So the line speed is really, really important to make sure that we get this sorted out. So now once we get past the line speed and we get a better understanding of what you're doing, then we come to another decision tree, if you will, where we have two places we could go. We could go with a fixed width electrode, either insulated or metal, or we could go with a variable width electrode, which again is either some sort of segmented system, right? Depending on the width of the segments and the configuration, that'll be determined. And so your application details help us determine that. So let me give you another example here. Let's say we move away from a blown film line and we go to a cast film line. And the cast film line is designed for a 2-meter width, and that's it. If you got a cast film line and you're running 1,000 feet a minute, you're set up to run 2 meters. That's what it's going to be. It's not going to change. In that instance, there wouldn't really make any sense to provide you a metal electrode that was adjustable. In fact, there's an argument, an easy argument that would say that'd be kind of a dumb idea, because if an operator made a mistake and accidentally adjusted one of the electrodes so that treatment didn't occur there, you'd never know it until it got to the winder, or maybe until it got to your customer, which wouldn't be a good thing. So in that example, a fixed width electrode of either a ceramic or a metal style is likely the best choice. But now let's move back to the blown film example. Many times in blown film, material is used for many things, some of which are bags or pouches or things of that nature. And furthermore, some of those things, those end products, don't want to be treated in its entire width. So if I again had a 2-meter blown film line, there may be times and products that you don't want that entire width treated. It causes some downstream problem. Maybe it causes an issue with your downstream customer, whatever it is. But that's information we need from you so that I can then provide you a piece of equipment with a segmented metal electrode that is suitable for your application. So as we go through this example, you can see when you go to our next slide, Mark, with the fixed width ceramic electrodes, this is typically used in converting applications. You don't see it used often in film extrusion. It's not that it doesn't work, or it's just not used, because of some technical reason. It's typically not used because in your converting customers, they don't want to take a risk of somebody misadjusting an electrode, a segmented electrode, and converting, and now all of a sudden they find it after the product's been printed, let's say, or they have a failure in a lamination because an electrode was misadjusted. They can't have that, right? The second reason you don't see these segmented electrodes used in converting is because many times in converting lines, they can run both non-conductive and conductive substrates. And you can't treat a conductive substrate with a metal electrode. So fixed width ceramic electrodes are typically used in printing, coating, and laminating, and occasionally could be used in blown or cast film applications. So now let's shift a little bit further and go back to the extrusion side and look at the benefits of certain electrodes and why they are used, or what would be the reasons for using them. So let's take a look at these ceramic electrodes, and I'm going to specifically call out a cast film application, because most of the time cast film applications are a known width. The die is set up for a given width. That's what the line's going to run, and there you go. So then the question becomes, okay, Tom, I have this cast film line, I run 1,000 feet a minute. Why do I want to use a ceramic electrode there versus a fixed width metal electrode? In that case, a ceramic electrode may be better suited simply because it provides a type of corona that's more suitable for the material. So what I'm getting at is, if for the same width, at the same power, with a ceramic electrode, I'm going to have a very uniform, dense corona that's not going to have a lot of filaments. You're not going to have a lot of little arcs and sparks. This is really important if, let's say, your cast film line is doing embossed film that are used in personal care or hygiene products. Because as you know, those products are very thin. The embossing makes it even a bit thinner. And of course, if you have a fixed with a metal electrode in that case, you could run a risk of pinholing or damaging that film as a result of arcs or sparks if you're using a metal electrode. So depending on the details of your cast film, in our example here, will drive the decision to go with either a fixed width insulated or ceramic electrode or a fixed width metal electrode. And again, this all depends on what the details are of your particular application. Now, fixed width electrodes with covered rolls are used all the time. This is a very common thing. And of course, if you don't need to lane treat or adjust treat at all, then having this sort of fixed width electrode, whether it's whatever shape it is, the shape is really not relevant here. It could be this rectangular or square tubing shape. It could be a series of round rods or tubes or something like that. Mainly the difference between those shapes and those designs, when you strip all the advertising away from it all, really comes down to power dissipation. Depending on how much power we have to deliver to the web at the speed that you're wanting to run, will drive really the style of this fixed width electrode. And that's, at the end of the day, that's it. They'll all treat adequately. They'll give you good die numbers. They'll be fine. It's really, from a mechanical and design standpoint, will drive the geometry and the style of metal bar for that application. And along with that, speaking of unique applications, have any of you, or how many of you, have considered in a blown film application a pattern, lane, or skip treatment application? And some of you, this might be new news to you. You might not be familiar with this. Well, if we go back to a segmented electrode style, for an example, where let's say we have, again, a 2-meter width, let's say we have 1/2-inch wide segments in that electrode assembly. So basically, you can engage or disengage a treat lane every 1/2 inch across that 2-meter width, okay? Think about that for a minute. So what that means is you could lane treat. So like in the illustration here, we could have lanes of active treat width alongside of lanes with 0 treat. That's one method. Furthermore, we could take it a step further. Let's say we only want to treat in an area where printing is going to occur, right? So we have this area. It's like a defined space in the web direction that we want to print, and then we want to skip. We don't want to treat in that area for various reasons. Maybe you're heat sealing or whatever the reasons. That's skip treatment. We can actually turn the treater on and off in microseconds just to get it to turn on, turn off, turn on, turn off, to give you basically blocks of treatment area. And then finally, we can kind of combine all this together and give you the ability to come up with a pattern treatment. So there are many options available to you in a sort of unique way in film extrusion where you can come up with these examples. Now, many times these things are done in conjunction with an inline converting process, right? So if I'm making bags, let's say, and I blow it, I gusset it, I treat it, then it's going to go into some kind of printing process. At that point, all these systems work together so that that treat area or that pattern or whatever we've designed there works specifically for the job you're running. It's an interesting process. It's very not used all the time, of course, but it is out there and you should know about it. And that's the reason I put it in this presentation today. So now let's circle back a little bit to the segmented electrode. And this is really sort of the bread and butter part of treater designs that are used in blown and cast film, mainly blown, sometimes in cast, okay? So what you see here in these illustrations, these photographs that are on this selection are various types and styles of adjustable width electrodes, and they come in all manner of different ones. And at the end of the day, they're all kind of doing the same thing, which means that you can adjust where you want treatment. You either want it here or you don't want it there. Where Mark's got the arrow right now is a perfect example of this. It's a great photograph to show this. We have a full width electrode here, and this full width electrode is got an area in it that has no treatment. So as you can see, you have corona on either side of it, but no corona in the middle. And that would be suitable if, let's say, we're gusseting bags and we don't want treatment where the gusset's going to land because we don't want the bags to stick together. And that's a perfect example. And so there are just a lot of different variabilities to this concept, but at the end of the day, they're all doing the same thing. They're giving you the opportunity to put treatment where you want it. Now, the other part of this that you guys don't see, kind of behind the scenes of this, is, and we get this question a lot. You say, well, we have two different segments sitting in front of you here in this picture. One are 1/2 inch wide segments and one are 1/4 inch wide segments. And let me again go back to this 2 meter wide or roughly 80 inch wide electrode. So why would you use a 1/4 inch segment in one case and a 1/2 inch segment in the other? Believe it or not, a little test for you here, it's due to the line speed. Can you guys figure that out? Why would the line speed matter relative to the width of the segment? Well, it matters because of power. When you gave us a line speed value of X, we took that, we applied it across the board, and now we know how much power at that speed is required. Now, if you gave me a line speed value that was, let's say, a little generous, my power supply might be, let's say, 10 kilowatts. If you gave me a line speed that was less than that and therefore a little more accurate, maybe my power supply size is only 7.5 kilowatts or 8 kilowatts or 6 kilowatts, okay? Which means that at a lower power setting, I could get by with smaller segments. So as we said earlier, the speed drives a lot of these decisions up front, which then drive the design of the electrodes themselves, okay? So it's very important to give us an accurate line speed. Furthermore, this line speed value, because it is so important in the size of the power supply, right? It dictates the size of the roll, and then further also dictates what kind of insulator is going to go on the sides of that roll, which dictates the economics of the treater. So again, in my example, if 10 kilowatts is never needed because maybe the line speed value was a little hopeful, everything else in the treater system is designed to dissipate 10 kilowatts. The electrode assembly, the insulators, the treater roll, the insulation, whether it's a silicone or a ceramic roll, that has to be determined by that power setting. And then on top of that, if I had to have a big roll to dissipate a bunch of power, now I have to drive the roll. So now I have additional costs. I have to have a drive, maybe I have to have a nip. Maybe the power supply is so big that I need to think about water cooling that treater roll. Again, more cost, more infrastructure has to go into that treater. So I think it's important, that line speed number is really important in this discussion, and I can't overstate that really, because as you can see, it really affects everything. Now, we were talking about the roll covering here and the impact on roll covering, and again, very, very important. The two most common roll coverings that people use on corona treaters and film extrusion applications are either silicone, and that can either be considered a silicone sleeve, some of you are familiar with that, or a vulcanized silicone. It's the same material, but it's basically, you know, permanently attached to the core of the roll. And then the other common insulator is ceramic, which is a plasma sprayed material, and it bonds to the surface of the roll. Both are suitable in just an insulating perspective. They both give you good insulating characteristics, but in an industrial environment where, you know, guys are walking around with knives in their pockets and stuff like that, tools on hand, ceramic is really the best choice here for durability. Silicone is good for a cost, you know, economics is good, but for durability and performance, you really want to shade towards a ceramic coating on your treater rolls. So it's just something to be aware of. They do both work. They both provide the insulating capability, but from a life expectancy standpoint, ceramics can be better. Durability is going to be better. Silicone is suitable, though. It will work. It will do its job, at least for a period of time before it, you know, it breaks down and then has to be replaced. So, okay, what power supply, right? What do we do? How do we run? What size power supply do we use for your application? Well, as I keep telling you today, it's a speed number, right? Your line speed is really important to us because that is what really is going to drive the size of the power supply. You know, Enercon and our fellow compadres out in the marketplace that make corona treating systems, all of us have years of experience doing this. We're all pretty familiar with what it takes to treat a polyethylene substrate or a polystyrene substrate or a polyester substrate. We're pretty good at that. Really, what we need from you is we need to know how fast and how wide and how many sides. And once we understand that, that will then drive us to put these details into a watt density formula, which will then help drive the power requirement. It all comes down to this. And once I know the details and I can calculate all this out, then I can choose the correct power supply in kilowatts, and then everything else comes from there. The size of the treater comes from there, the size of the treater roll comes from there. Everything is driven off that decision. And so you might say, well, really, you know, how does this play out actually? You know, what's a real example of this? And Mark, going to the next slide, we show it here. So when you have different substrates, and this is a common mistake people make, it's not intuitive, right? Different films respond differently to power. So this slide here is really, its purpose is to prove this or to show this, illustrate this to you. We have a pre-treated polypropylene, we have a polyester film, and we have a polystyrene film. And I purposely picked sort of hard, kind of easy, and super easy films to treat, just to illustrate a point, right? So each one of those comes and starts at a different dyne level out of an extrusion process. And then when we treat them at the same power setting, they all end up at a different dyne value, okay? So as you can tell, when we size a system and you give us a random list of materials, like I have linear low, I have low density, I have high molecular weight, high density, I have medium density, and then you'll say, some of this stuff is high slip film, some of this stuff is zero slip film. So I have to look at all these variabilities, and maybe you'll even throw in there like a polypropylene film or something of that nature. You know, I have to look at all that and then make a decision, because I know, based on this example we show here on the screen, that none of this stuff is going to treat exactly the same. I can give you the same dosage of energy, but the net end result is going to differ. And so again, the line speed is really important here, because on our end, we're not doing our job correctly if two things happen. I didn't do my job if I provided you a power supply that you only use 20% of, and 80% of it never gets used. And equally, I did not do my job if the treater is the bottleneck in your line. meaning my line speed's limited because I don't have enough power. So it's this balance that I have to constantly make, and your element to this responsibility is line speed, right? We have to have the correct line speed going forward. So once we get past all that, then how do we run this process to make sure that it's doing what we want it to do? And that's where the features and controls of the power supply all come into play. And today it's better than ever. It is absolutely better than ever. In the past, you would have this sort of assortment of tag-on boxes and enclosures that we dotted, all around the treater that might be blower controls, it might be a separate controller for the drives, it might be a separate switch box for pneumatics, it might be a high voltage switch, it might be, any number of these things, right? All that stuff today is incorporated and built right into the HMI of the power supply. So it's like one-stop shop, right? You walk up to the power supply, you look at the screen, and you can identify virtually every one of these things that are, a part of your line. So controls, features, ease of interaction, awesome. Today is the best time ever for Corona treater power supplies and controls and operator interface with all of that.
All right, thanks, Tom, for all those insights. Before we get to our audience's questions, just a quick recap of some of the key concepts. Film should be treated both at the time of extrusion and retreated prior to converting. Your application variables such as line speed heavily impact machine size and cost. We looked at various electrode designs for fixed width and selective area treating. We talked about the importance of balancing economics versus durability when it comes to roll coverings. And we reviewed how power supplies are selected based on power level and the needed feature set. With that, we will get to your questions. Reminder, parts 2 and 3 of this webinar series are coming up in June, every other week for a period of time. And we've got our first question here, Tom. If I run different films that respond differently to Corona, what is the operating range of a Corona treater? How much can it vary?
Great question. Most modern day Corona treaters have a pretty wide operating range. So for example, I'll give you a really simple example here. Let's say you have a 1 kilowatt or a 1,000 watt power supply. Well, that power supply can easily run down to 100 watts, maybe even less. But the other part of your question, which is also interesting and important to know, is part of that is also the design and the implementation of the electrode that we pick. So if you, for example, if you gave us, again, going back to a line speed number that's not accurate, so we had a big power supply, right? And you're only really needing 20% of it. Well, I had to build the electrode to deal with 100% of that power. So now you're asking the electrode to dissipate only 20% of its ability. Sometimes those mismatch opportunities create trouble, right? They just, it's like trying to shove a 4x8 sheet of plywood into the back of a standard sedan, right? It just doesn't work. And so again, the line speed is important here. So we size the power supply right. If we size the power supply right, then not only do you get the right turn down, you have a lot of range in terms of operation, and you get a good uniform Corona.
Thanks, Tom. Next question is, can you talk about why stainless steel is recommended for segmented electrodes?
Yeah, the stainless steel has been chosen over the years because some of you may remember this. If you go back any number of years, the default material was aluminum. Aluminum segments were used all the time. Aluminum bars. That was the material of choice. It was used mainly for one reason. It's relatively easy to machine. It's inexpensive altogether. Good to work with. Lightweight. It has a lot of benefits. But the one thing it does not do well is manage thermal heat. So again, let's say we're trying to dissipate this 10 kilowatts on this 2 meter wide line. If I have to dissipate 10 kilowatts, I'm going to have a mass of metal out there to get rid of it. I gotta be able to have the treater station designed in a way so when you turn it up to 10 kilowatts, the entire electrode can dissipate 10 kilowatts. If I do that with an aluminum electrode, which I can, that electrode gets hot. One of the side, the side things of corona treating is ozone and heat. And that heat's got to be managed. And of course, you manage it better with a stainless steel material versus an aluminum material. Now, how does that actually manifest itself in your application? Taking that 10 kilowatts, having the air gap of the electrode set at 60 thousandths, let's say, you have both electrodes next to one another, stainless, aluminum. When that aluminum starts heating up, it twists, it starts moving, so it changes the air gap relationship between the surface of the electrode and the ground roll. In this stainless example, it does not. Stainless is a lot more thermally stable than aluminum, and so therefore you have less application problems going forward. You know where you would in one case with aluminum, you could have the air gap really close in one end, further away in the other because of the way the electrode shifted around, and you'd get potentially uneven dyne levels across the width of your film. So for the most part, and there are exceptions of course, but for the most part, many of us have shifted most of our product offerings from aluminum over to stainless steel.
All right, Tom, looks like we have one more question. This person wants to know, can they future-proof their line by simply buying a power supply with a higher kilowatt output?
Well, you could future-proof your line by doing that, but then the second thing you'd likely have to do is future-proof it by making a bigger treater roll, right? So let's use my example again. I have a 10 kilowatt power supply that you say, well, I don't need all 10 kilowatts today, but I think I'm going to need them in the future, right? Right now, all I need is 5 kilowatts, or maybe all I need is 7 kilowatts. I cannot dissipate 10 kilowatts on a roll that is suitable for 7 kilowatts or 5 kilowatts. I can't do that. So what would I do? Well, I could build the treater so that the roll diameter and the corresponding wool covering is good enough for 10 kilowatts. I could build you a 10 kilowatt power supply, and then the power supply has enough range so that you can run it anywhere you want. The one thing I would say to you about that is there may be diminishing returns on that idea, just depending on how this goes. So I'll give you an example. It works really good. The idea is really good. In both the kind of normal size power and then the future power, if both of those can be done with a single electrode assembly on each side of the web, assuming we're talking a two-sided treater, great. But what happens if, once I got to the bigger power supply for the future, it requires more electrode assemblies, like 2 per side? You've really changed the economics here, haven't you, right? This treater got really big. I'm paying for hardware I'm not really going to use. You know, in that case, you want to consult your supplier on this and have this discussion, right? Because in that case, the economics and the physical sizing of the treater and so forth, it may not make sense to do that. But going back to the idea, if both power supply sizes, you know, this normal size and the slightly bigger size, if in both cases it would be good for just a single electrode assembly on each side, great. That's easily done. And maybe the only other change to the treater station at that case might be just making the ground roll a little bit bigger. Again, doable, right? There's cost there, but it's not horrible.
Excellent. Thank you for that, Tom. And thank you to our audience for joining us today. Everyone will receive access to the recording of today's presentation as well as the slide deck in an email tomorrow morning. You'll also be receiving your credentials to the second and third parts of this webinar series. If you have any questions, please feel free to reach out directly to Tom or send us an email on any topic that you may want to make sure that we cover in the future. Again, we appreciate your time in joining us today, and that will conclude today's webinar. Have a great day.